So what happens if we're studying an equilibrium reaction, and we know the macroscopic properties don't change, and it can be pretty hard to detect things like color anyway. So what happens if we're looking at it and we want to know if it has already reached equilibrium or not? Okay, that's where the reaction quotient Q comes in. So Q measures the relative amounts of reactants and products for a reaction not yet at equilibrium. We can use Q, and if we know what the equilibrium constant for a reaction is supposed to be, we can use Q to compare it to Kc, and see how close the reaction is to reaching that equilibrium and which way the reaction is going to go in order to get to equilibrium. So the calculation for Q is actually the exact same for Kc. So Q is our concentration of our products raised to their coefficients and multiplied together, divided by the concentration of our reactants raised to their coefficients and multiplied together. So the same principles of calculating Kc also apply to Q, but we call it Q the reaction quotient when the reaction hasn't reached equilibrium yet. So to summarize our meanings of Q before we jump into a few examples, if we calculate a Q, okay, and it's equal to the equilibrium constant, that means the reaction is at equilibrium. So our rates of the forward and reverse are equal and no net reaction occurs. If Q is less than Kc, so let me write down again my Q value here, equation, which we know, so this is just for our generic reaction above, and this is also equal to, or we know we use the same calculation to calculate our Kc. B, so if Q is less than Kc, okay, so if Q is smaller, what that means is that the reactants are most likely larger and the products are smaller than they actually need to be to calculate Q. So the reactants are currently too large, so if Q is less than Kc, the reaction proceeds to the right in favor of the products. So since Q is too small, the value of Q has to increase to match that of Kc at equilibrium, which means the reaction is going to go to the right because we need the amount of reactants on the bottom to decrease, and we need the amounts of products to increase in order to increase our value of Q. The opposite is true. If Q is greater than Kc, then the reaction proceeds to the left in favor of the reactants. So again, if Q is too big, we need to shrink Q. We need to decrease it to get it down to the size of Kc. So in order to decrease Q, we need to shrink the amount of products we have and increase the amount of reactants. So to do that, the reaction will move predominantly to the left in favor of the reactants. So we'll have a net reaction to the left. So Q can tell us which direction the reaction is proceeding currently, and again, how close it is to reaching that equilibrium. Let's look at a couple of examples of using and calculating a reaction quotient. So consider this reaction. H2, we've seen this in the previous video, so H2 plus I2 goes to 2HI, for which the Kc is 49.5 at 440 degrees Celsius. So the reaction quotient is calculated at various times. Okay, so what's happening here is we have a reaction that's occurring, an equilibrium reaction. We want to know if it's at equilibrium. So we wait some amount of time, which we just call time 1. We take a sample of the reaction and we calculate Q using the sample to see if it's reached equilibrium. If it hasn't, we wait for a later time 2, to then again test our sample and see if the concentrations now match what the concentration should be at equilibrium. So what we want to do is calculate Q for both time 1 and 2, and then predict whether the reaction will proceed in the forward or reverse direction for both of these separate experiments, one at time 1 and one at time 2. Okay, so for the first experiment, and we can calculate our Q value. We'll call it Q1 since we're using time 1. Our expression here is going to be HI squared over H2 times I2. Okay, and that gives us, let's see what we have, 0.300 squared on the top. On the bottom, we have 0.0250 times 0.0350. And when we calculate that, it gives us a Q value of 103. Now looking at this, we have a Q of 103, so we know that our Q value is greater than our Kc value. Our Kc value is here at the top, 49.5. So 103 is greater than 49.5, which means Q has to decrease to equal Kc. Again, in order for Q to decrease, we have to, we want it smaller, so we have to reduce the amount of products present and increase the amount of reactants present. In order to do this, so decrease the products and increase reactants, that means the backwards reaction is the one that's actually occurring. So we would say the reaction, net reaction, is to the left, okay, or net reaction to the reactants side. And we then can calculate our Q for our second time. So we've taken another sample of this reaction. Later, we know it hasn't reached equilibrium yet. So we take another sample. Let's see if it reached equilibrium now. So it's going to be the same expression. That doesn't change because we're using the same reaction. So we can fill in our values. 0.244 squared divided by 0.0300 times 0.0400. Okay, and when we calculate that, we end up with a value of 49.6. So within measurement error, it's safe to say that our value of Q is equal to our value of Kc in this case, and we can say that our reaction is indeed at equilibrium. Okay, so that's how we calculate Q and how we can use Q to compare it to Kc to see where a reaction is. Let's take a look just for practice. We'll take a look at one more example. So in this one, we have a reaction with a Kc of 1.7 times 10 to the 2 at 500 K. So this is the Haber process we're looking at here. We'll study this more later. But nitrogen plus hydrogen to produce ammonia. Determine what direction the reaction will proceed given these following concentrations. So again, calculating Q, we don't know if it's at equilibrium yet, so we'll calculate our reaction quotient. Here we put our products on top, so our products in this case are NH3, and we raise that to its coefficient, so squared. The denominator we have N2, and we have H2 cubed. Okay, now we're just plugging in our values. So we have on top is 8 squared over 1.5 times 1 cubed, and that gives us a Q value of 42.7. Okay, so we get a Q of 42.7. Now in this case, our K is initially 170, so we know that our Q is in fact less than our Kc value. So since our Q is currently smaller, that means the reaction needs to proceed to increase the value of Q. To increase the value of Q, we need to increase our products and decrease our reactants, which means the net reaction is predominantly to the right. And that's about it for studying the reaction quotient and how to use it.